Hi guys. I was actually talking now and I just realized my mic was muted. So I'll probably have to repeat myself here. So what we were given here, we have a 120 amp, 120 volt source, and it's applying three different loads there, namely Z1, Z2, Z3, and they are expressed there in polar form. What they're requesting from us is they want, assuming that when the switch is open, that the total current I, that's the one. So when the switch is open, the current I, the power factor, the real and the active and apparent power supplied by the source, right? So obviously that's be coupled to that. So what I was asking is that if the switch is open, obviously we can ignore Z3. Is that correct? Fantastic, right? There's no. Hi, Mr. Breed. Good to see you on. Obviously, that means no current flowing through that. So, all we have to basically do now is, calculate basically the current, the total current. Obviously, this is a simple parallel system, and we've done something similar to this before. And we can just say I1 will be equal to 120, the angle of 0, and the first one is going to be 5 at 30 degrees. And we're going to have I2, that's going to be 120, also at 0 degrees, and it's going to be 5 and 45 degrees. And of course, I will just be the vector sum, or the sum of these over here. So can you just give me I1 and I2, please? I think my pen's a bit thick here. Just give me a moment. Just get this just thickness. Okay. So someone just give me I1 and I1 and I2, please. So for I1, we get 24 at minus 30 degrees. Obviously, that's an inductor, as you can see. And over this is a inductor. What is this over here? Definitely also another inductor. So 20 divided by 5 in essence, and it's 24 at an angle of negative 45, also inductor. And obviously, all we have to do to find I, right, which is the total current, assuming that the switch is open, we have to calculate obviously now the total current here. Okay, so let's see. Well, what do we get for the total current? Is it both 24? No, man, it's 20, sorry. 120, what? No, 120 divided by 5 is 24 also, okay. Yeah, it's all the same, sorry. The breadth is got it, that's 47.589. 47.589. At which angle? Minus 37.5 degrees. Cool. What is it? 2. Guys, what is the answer there? 24 minus 30 plus 24, 37.5. You should get an answer of 47.897. I get 897 at 33.75. Can we just confirm that answers? Is it 47.5? Is it 589? I'm getting a different answer. Let me just confirm. Minus 30 plus 24 at negative 55. Yeah, it's 589 at 37.5. Okay, cool. That's correct. Are we all happy with this? Now the next step is for you to find your parent power, your true power, your reactive power, and a parent power. So VI cos phi, VI sine phi, and obviously V times I. Cool. So our total voltage was 120. What is I? I is given as 47.589. And can someone tell me what angle must we use for cos? That's cos. Which angle must we use? Yes, the 37.5, exactly 37.5, which is that angle there. So never forget what the power factor is. In fact, the power factor for this, they did ask for the power factor before I jumped the gun here. Our power factor is equal to cos negative 37.5. Obviously, you can do that. That's a quick one. There's obviously 2 marks. So I don't know. I'll mention that now. 37.5. And you get 0.7934, and this will be lagging because it's negative. So I want to make you aware, especially with power factor, I typically allocate a mark. I'll show you now. Sorry about this. Give me a moment. A mark here and a mark for lagging or leading. Is that clear to everyone? So that is how I typically give my marks for this particular question. Or maybe I just give 1 full mark. Cool. So let's get our power. And obviously you can work out your reactive power as well. So let's have a look. It's equal there. So what I get from a power, in watts, let's see, 30.59. Yep. The reactive power, this will be var, and this will just be volt amps. So let's see what we get there. So what is my reactive power, Q? It's a Casimiro. Okay, the precise color for us there, it's negative, and that's very correct. It's very important with the sign there, negative 3,400 minus 3,476 point something. And obviously this tells you that it's inductive, right? Very important. And then your parent power will be, what is my parent power? It will just be your volts times your amps, and 5, 17, 570, 5,710.68 volt amp. Okay, so just as an alternative, if I just had P and Q, I'll show you now. What I typically like to do for P and Q, you could have just you just have to go mode, complex, obviously. I'll type in the 4, 5, what was again? 4, 5, 3, 90, 3.59 minus times what's my reactive power again? 3476.441. Move it multiplication. So equal. So I put it into rectangular form. I just go shift, complex, number 3, then boom, I'll get my reactive power with my, obviously with my power factor there. You guys see that? You guys follow that? There is another way of actually just doing it. Fantastic, cool. So let's go back to the board, and then I'll share with you again. So you can see it's still the same stuff, but obviously we're just adding just more detail now on more detail on now we can find powers now and stuff. Obviously we found the phase angle before, now we know what the power factor is. Cool. So again, just to express this all as a complex number, and this will be negative. That is why obviously the sign is important. 3476.441. And you just convert this into to polar form. Okay, cool. So that's part A of the problem. I will not do part B. That's for homework for yourselves. I'll just have to continue with the lecture now, right? Okay, so I just want to share this. Yeah, so this is the question. I did say solution is to be posted, so it will be part of your homework for this week. And make sure you do B and do C, right? Also, there's another sum as well. You can do, obviously these are very, you could say test level type questions maybe, or yeah. And I expect you to do the single phase electrical loads as well. Another type of, another problem you can do. So these are quite nice problems actually for 3-phase power and so on. Anyway, so if you can do those, and then yeah, that'll be homework. I'll post some more homework on this as well. Okay, so just a small section. This is on page 775, and sometimes they'll give you this type of question as well. We have multiple complex loads, right? And obviously we are doing something similar to this in a way, but what is important to note is that so what I mean is it's a question like this. So we just have these block diagrams, And the way you can view this is simply like maybe it could be in series or parallel depending, but I mean that's typically represented as a block diagram, and they're just showing the load with inductive or capacitive. Sometimes they don't tell you if it's inductive or capacitive, but it would simply give you the sign. So all we have to basically do for a question like this is it's quite simple. All the powers we add, like we've done before individually, and for the reactive power, obviously we also add them up algebraically, but the thing is we must be aware that the inductive will give us a negative reactive power, which we've obviously seen in the previous questions, hence me coming up to this point where the negative or lagging, and in terms of the capacitive power it's going to be positive. It's very important to note that true power, because that's essentially the resistance component, is always in phase of the voltage, and it will always stay positive. So just to quickly do this example for you on here. So I'm going to show you also for the test. Make sure you practice these ones, this one, and that one. So it's three. It's from exercises as well. There's also one like that. But I'm obviously just showing you the approach on how to tackle these problems. So make sure you're able to obviously solve these problems, and you can see they're actually coming from question papers and so on. So it's something you don't actually need past papers, but obviously whatever I show you guys and what I recommend you practice on, prepare them. So obviously over here, and obviously once it's complete, you guys can actually get the answers as well. I'll do example 4, and I'll do it on the slide. It's quite easy to do. So like I said, all we have to basically do is add the powers up. Right, so it's the same as having a circuit essentially, but it's just kind of a more convenient way to actually just do it. I'm not sure why they actually included this here, but anyway, it's part of the content. So you have multiple loads, and then what we have to do is look at the total power, and all it is going to be power of the first load, power of the second load, power of the third one. So we keep power, it's positive. It's always positive. True power is always positive. In this case, 300, 475 plus 150. And if you tally all of those guys up, you get 925 watts. So Q, and this is the fun part of it, is obviously now we have to look at the 650 var, 111 var, and the capacitive. All we're basically doing is, if it's inductive, it's going to be negative, as stated. It's negative, and if it's capacitive, right, leads the voltage, and we have to add 375. And once you have all of this, you add them up, you should get an answer of minus 1375 var. And obviously what they're looking for is the apparent power, and we've obviously been doing this, and we know that S equals P plus J8, JQ, and all we have to basically do is say 925 minus 1375. That's 4 volt amps, sorry. And then once you convert this into polar form, you get your answer of 1657.2 at an angle of minus 56.07. Right? They're asking for the power factor. The power factor will be over here. So this is the power factor. The power factor, if you look at the previous thing we did, the power factor is attached to the apparent power. That's the total power factor of the whole supply. What this also means is that the supply itself is pushing out 1657 volt amp, and obviously at each circuit or each load, whether that's a motor, for instance, and that is some capacitive bank of God knows what, and the inductive, obviously, okay, this is the capacitor where that's generating reactive power. So over here we have, it consumes minus 650, it consumes 11, obviously that generates. So in essence, our voltage here supplies 1657.2 volt amps. And to find the power factor, it's just a simple matter of saying, obviously, your power factor will be because of that angle over there, 56.07. And because it's negative, it's going to be 0.5582 lagging. Is it clear to everyone? That's all for that song. It's just another type of a more easy thing to do. It gets more fun in I think it's because it's partially done in electricity. Well, it's done a lot in electricity, but I don't know. Is there any questions with this one? But it's just an example 7.3. It's just a different type of question. Kind of straightforward. We don't have to actually work out all the individual fault dynamics. Any questions, students, with this particular problem? Viavanga, Garcia, Kitongo, Casimiro, Duplessis, Mr. Ford.
Yes, sir. Yes. Yes, the angle shouldn't be minus instead of.
Yeah, it must be minus. Yeah. It's the same, man. Let's not put lagging there. Yeah. It is minus, but let's not put lagging. Lagging means negative. Leading means positive.
Okay.
But I mean, you can put negatives, no problem. I'm just saying to you that I know. Yeah. Very important. Lagging is negative. Leading is positive. But I'm just showing you. This is like a sub problem where they give you different, like for instance, and I highly recommend you practice this, especially with the upcoming test. There's one practice here. There's another one here. There's another one there. You see, it's just a variation of the problem. But obviously, you see here it says 3-phase. That's a single phase, and it's a 3-phase. And once you do 3-phase, you'll be able to, even see that assumes a single phase. You can assume that a single phase first. But once you do 3-phase, you're able to tackle it very easily. 3-phase is not that different. Not that different, but I mean, it's you'll see once you do it. Let me not say too much. But try just assume that it's single phase. Cool. Okay. And why is it not there? And I just literally added this. Okay, right. So now we're starting on the last section of this. And it's talking about power factor. So I think before I actually start on power factor, on this low power factor, I wanted to open a research article for you. And you know, I would like to incorporate this element within my work of research to give you guys ideas of just give me a moment. You know, like getting our paper and being able to get information. But anyway, it's fine. So I just wanna just close a few things here. Okay. She would. Oh, yeah, you are. Okay. Moment. Yeah. So I'll share this paper with you. Just a quick few minutes. Yeah. So here's a paper published in 2019. And it talks to a comprehensive review of maritime microgrid system architectures, energy efficiency, power quality, and regulations. Now, the keyword that I'm trying to talk about here is power quality in particular. Microgrid meaning just a small grid which is on board essentially, compared to like the one on land, for instance, which is obviously a massive grid. Cool. There's nothing important yet, but I mean, yeah, they're just talking about different configurations, you know, in terms of how you're coupling your propulsion systems. And obviously, we're moving toward a hybrid type where the motor, you've got a generator and got your power converter, and it's coupled directly to the load instead of the old standard, you know, propulsion gearbox or your fuel coming in, gearbox or the diesel engine and then coupled to the propeller, whatever. Obviously, there's a few other things to talk about, the architectures of how a simple passenger vessel will look like, where we have this kind of supply. You're generating around 690. Well, this is at the 60 hertz, obviously. This is probably an American. Obviously, you have a transformer here, stepping it down to a 444 to 60. And they're just showing you the transformers, the diodes, and it's a capacitor, obviously, then some form of I think that's some transistor type. I must be careful. I just can't recall now. Some electronic thing, but I'm not particularly focused on all of those. what I want to talk about is the power quality component, right? So power quality is something important, and here it's just some I'll read the text basically, but the most important part of power quality, and I'm looking for this particular thing, okay, is there's also standards to which the power quality must be adhered to. Now, I've shown you this kind of stuff before in other standard, the IEEE 45 standard, but there are things to do with your frequency should be within 5%, 5 to 10% deviance, negative or positive. Similar with your voltage, it can only vary between those three things. And part of the power quality is also your power factor. Now, I'm having a look at something. I'm looking for this thing. So I was actually wanted to show you something, but anyway, I think the main point is that part of power factor is part of power quality. Okay, yeah, you're talking about here. You have to look at your basic power balance rated in all operating conditions, your power quality, your harmonics, your voltage sag, your unbalanced conditions, your electromagnetic, your dynamic performance, which is regulation, frequency ranges, and your transients. Okay, cool. This is quite interesting, but power factors are for power quality, and I want to just actually show you that there's a specific limitation you need to get for your power factor. Otherwise, your supply is deemed, inefficient. Anyway, that was something people want to just show you. Anyway, so just like anything, like I said before, not everything is going to be 100%. You're going to lose a few things, and I want to talk about a low power factor because a low power factor is possible, right? So they're basically showing the formula over there for your single phase supply, and they develop a relationship putting current as the main variable, as the independent variable, and have all the others dependent. And they say it is clear from a fixed power and voltage, so we're keeping that constant, that the load current is inversely proportional to the power factor. And so what it means is that a low power factor results in a higher load current, and vice versa. And a low current gives you a higher power factor. So your power factor less than unity results in the following disadvantages. So what we're saying here is that if you don't have 100%, obviously you'll never get 100%, but 100% or power factor of 1, having a poor power factor, and this is why it's important to know this. This is the result on the equipment. So number one, it says the electrical machinery, your alternators and transformers, even the switchgear is always rated in kVA, right? And the reason why they rate that in kVA, like for those particular equipments, they say there is that in blue text that because we don't know the load, we don't know the kilowatt, right? So say the power factor of the load is not known when the machine is manufactured in the factory. So we don't know how it's going to behave once we all connect the equipment together. And what they say there, if you look at that ratio of kVA, which is essentially your watt full power divided by your cos phi, your power factor. So it's clear that the kVA rating of an equipment is inversely proportional to the power factor. So if the power factor goes up, then your kVA goes down. So if your power factor is very small, the larger the kVA rating. And what it means is that even if when you're running equipment, it will draw more power. And they say that therefore, at a low power factor, the kVA rating of the equipment has to be made more, and making the equipment larger and expensive. Obviously, that's for manufacturing. But you guys understand what a power factor does. So what I'm saying is you're running a motor inefficiently, and let's say the power factor is low. What it means, it'll draw more current, and consequently, it will consume more kilowatt. It will consume more volt amps or more apparent power. Does it make sense? You guys follow that logic? It basically increases the amount of supply. Amount of supply. Yeah, it requires more basically. Okay. The second thing is your conductor size, right? So they're saying to transmit or distribute a fixed amount of power at a constant voltage, the conductor has to carry more current. And I mentioned in the previous thing. So if you have a poor power factor, what could also possibly happen is obviously draw more current. And what they say, this necessitates a larger conductor size. So that is why you have to ensure your power, when you're generating your power on your alternator, it must be within a particular range. And if it drops so poorly, the current will shoot up within the cable, and obviously it will start burning. And they're explaining there an example. So they're saying, assume you've got a single phase AC motor having an input of 10 kilowatts on full load and a terminal voltage is 250. At a unity power factor, you divide the two, you get 40 amps. So if your power factor is at 0.8, what happens to your wattage now becomes 12.5. You say 12.5 divided by 250, which is the watts. It increases by a whole 10 amps. And what it means is that they're saying if the motor is now worked at a lower power factor 0.8, the cross-sectional area of the supply cables and the motor conductors will have, or now have to be based on 50 amps. And obviously, if it's a bigger current, we need a bigger cable. So that's another important thing to think about in having a poor power factor. And then the last few there, lesion 3, 4, and 5, is that we also get large copper losses. So bigger current results in higher I2R losses. And the fourth one is poor voltage regulation. And you will see this once we do the analysis in alternators, induction motors, and possibly transformers, even transmission lines, we all do, is that you find out that when you supply, let's say from the start of the generator side, you're applying 3,300 volts, you actually only end up getting around, let's say, for instance, 3,185, or let's say, or 3,100. So there's a loss in 200 volts. And they say there, obviously, if it's not right, in order to keep the receiving end voltage within permissible, extra equipment is required. And that is why we actually put your automatic voltage regulations, your AVRs, on the system because of the, if the power factor is too low. Last reason it says the handling capacity of the equipment, and what I mean there is that if obviously your motor is rated at a particular wattage, okay, yeah, and obviously it will reduce. It's back to the analogy of the reactive power. It will be a waste essentially. Reduce the capacity of whatever equipment you're running. So just as a point, we don't want a poor power factor. And this is the typical point here of power factor, and it says a low power factor is undesirable. In fact, normally the power factor of a whole load system is lower than 0.8. So in fact, we typically want a range from 0.85 to 0.95, or it can never be 1. So, and they're saying the following causes of low power factors are the following. They're saying AC motors, whether it be single phase or 3-phase, they have a low lagging power factor. So if you're running, these motors work at a power factor which is extremely small on light load, then rises to full load. So that is why it's very important for your motors to be run at full load, and not at basically at most of its capacity versus a light load. So if you might think you're running a load and you're running it light, even though it's rated less, you're actually generating more kVA. Things like arc lamps, electric discharge lamps, and your furnaces also operate on a low power factor. And last, they're saying the load on the power system is varying. So a low power factor, when the supply is obviously changing, all of that, it increases, it makes a low power factor. But anyway, this is just more. Okay, so yeah, we have a low power factor. Is it the end of the world? No. Fortunately enough, we have technology to reduce it, right? And when we talk about reducing or curtailing or mitigating the thing, we can actually, what we call is power factor correction. So if we have a poor power factor, we can actually improve it. Reading over here, it says power factor correction is a term given to a technology that has been used since the turn of the 20th century, and it's basically to restore the power factor close to unity as economically viable. This is normally achieved by the addition of capacitors to the electrical network, which compensate for the reactive power. So So obviously they give you a few benefits, and obviously these benefits are the inverse of these things. You know, like you require there's a smaller voltage drop. I squared all losses is low. We get more kVA, get more reduction in bowls. There's also things like that, and also environmental benefit because we don't require as much. How do we correct power factor? So I'm just giving a typical story. So if you look at what tends to happen, okay, so inductor load pushes it to the right, then we apply power factor correction and it goes to the left. Can you guys see that? So inductive load pushes it, we apply some power factor correction and it goes the other way. Can you guys see what's happening there? It first, or in this case, it looks like it's leaning, but you get the idea. So it pushes it out, and then we basically apply a power factor correction and try to get it as close as possible. You guys see that on the graph over there. Can you guys see that on the graph? Are you guys still there? Cool. And what you see there is that inductive load obviously will make a power factor, will shift the thing. And what we apply is what you're seeing there is something called a capacitor bank. And we're going to talk about it now shortly. And when you apply the capacitor bank, it generates reactive power, it consumes it and kind of lines up the voltage again. So I wanted to show you something here. There's like a moving diagram, but it's perfectly fine. So what I expect you to know as well is these techniques on how to correct power factor. It will form part of your test 2, so making you aware, right? The main 3 types on how to improve power factor are the most common types. And the saying is normally the power factor of the whole load on a large generating station should be around 0.8 to 0.9, right? And sometimes it is lower. We have to improve it. And the 3 methods of improvement, the equipment we use is static capacitors, a synchronous condenser, or a synchronous capacitor or motor, overexcited motor, and also phase advances. Right? So I might ask you, name 3 types of equipment to improve the power factor. So the most common one is a static one. And what we typically do, the saying there is that power factor can be improved by connecting capacitors in parallel to the equipment. Typically, you want to connect as close to the source of generation as possible. And there are some advantages and disadvantages over there. And I won't talk about all of that now, but that's the one type. And what it basically looks like, close to where it is, you typically going to apply it either in star or delta, but typically it's in delta, I think. You have capacitors, essentially something like that. Right? The third type is, this is an image of what happens here. In the first case is what we used to. Red will be active power, and so basically on the block, the rectangular block on the side, supplying those motors, and we have reactive power, active power, and then when supplied to the capacitor, it essentially, which is the green section now, the capacitor kind of capacitor basically removes that from the load in a way, or provides it actually. Then we actually get an increase in more power to basically use. It's a bit of a strange diagram actually, I'm looking at it now. The other type is a synchronous motor. I've posted this note as an additional thing, but it's particularly a synchronous motor with a leading current, and we're actually going to do synchronous motors next semester. And when it's overexcited, meaning the voltage is greater than the EMF essentially. Let's say an overexcited also running on no load. That's in that case. It's called a synchronous condenser. And typically we connect it in parallel with the supply. What's shown there, and what it does, it basically it creates, and you'll see it the maths behind this, and creates a leading power factor. Anyway, so that's the one. There also advantages of these, and they say they. I think the main ones. I think what's important is that obviously it produces noise compared to your static capacitors, and it has no self-starting torque, so you have to start up the motor basically. So that's the advantages. Still is worth mentioning. The other type is phase advances. However, they have a limitation on the size of the motors. So that's another type. So I'm not going to go too much in all of these, but just making aware there's the three common methods, or the conventional techniques. There are some more modern ones. I can't remember exactly what the other one was now. Which is quilting power factor. Okay, so basically we're at the last part of the lecture here. So let's do some analysis, some calculations on power factor. So it says we've already seen that the power factor is most often the result of more inductive loads and capacitive loads. Inductive loads are more common because everything works with electromagnetic induction, washing it all as a motor basically. We're saying thus it follows that we should be able to influence or improve the power factor by adding capacitors, right? Generate reactive power. These additional capacitors are added in parallel across the supply line. So I said more close to supply is where we want to add the capacitors. So for single phase system, it's given by that equation over there. So what is that equation? Where does it come from? Let me explain to you quickly using this diagram. Initially, just to show you, we had what they're explaining is that we have, this is the first setup, right? Look at, it's alpha number 2. You guys see that one triangle, this one here, right? You guys, we'll do a question. You guys see that? You guys see the red triangle? Cool, thanks. So that is our base case. That, let's say that's a power factor of 0.7, right? What happens now is that we want to obviously increase the 0.7 to maybe a 0.85, right? So what we actually do is supply capacitors, as the text says there, over here, right? So we're gonna, so this is the triangle. So we actually increase this part here. So we add, this is the capacitor part. So we add capacitors over here. Sorry. Capacitors over here, supposed to be capacitor. And what it does, it pushes up. That's why the arrow goes up. It pushes the power factor back to there. Does it make sense? So obviously the angle becomes smaller because cos 0, cos of 0 is 1. And if cos is 1, it'll be perfectly flush with P. It'll be perfectly in line with P. So does it make sense? So we initiate 0.7. Imagine this is alpha 1, this is 0.7. Alpha 1 is 0.7. So cos of 0.7 is 45.57. And if we increase it to 0.85, it becomes 31. So can we see that the angle becomes smaller? 31.79. Does it make sense to everyone? You guys understand what this triangle is trying to explain basically? Oh, they do it demonstrate here. Cool. Yeah. Thank you, Mr. Njana. Thank you, Mr. Duplessis. So basically how they get that formula here, they show you that they take the changing Q, which will be now the amount of reactive power required, times V times Ix. That makes sense, right? Cool. It's VAR or whatever. And then they say we know that IXC, with voltage divided by your reactance. Obviously, we've seen this before. And your reactance is then equal to 1 over 2 pi FC. So if you substitute XC into the IX over here, you get V2 pi F FC basically taking this IXC, substituting into back into equation 1, and you're going to get change in Q will be equal to V squared divided by 2 pi FC, and boom, if you divide out by the voltage, if you divide on the other side, that capacitance on its own, we will end up with for single phase system, it looks like that. For three-phase system, and you'll touch on that, it'll be 3, because obviously it's 3 different phases, hence divided by 3. But so your capacitance required will be change in Q divided by V squared 2 pi F. So I hope you guys got that. Right? Cool. So what we're going to do now is an actual example on a typical power factor correction thing, type question. Right? I'm just looking at what is next here. This is not what it's supposed to be there. Okay, cool. So how do we correct the power factor? So the first saying, our first setup, I'll just use it here. I'll just use this one as a, just put it over here. Okay, so I have one more for you to do. So over here, our first setup, let's just have it like this. We have 120 volts, 60 hertz, single phase, and then there we have our power, volt amps, and that. So we know that this is P. This is going to be 980. Your vertical component is always your active component, and this is 525 volt amp. Cool. So now they want to improve the power factor to 0.98 lagging, nearly to 1. So obviously we need to first find the first angle over here, right? And the first angle we can use cos phi equals P, is it, that's P over S. And my cos phi will give me how much? Can someone just calculate for me quickly? Can I have a power factor? Look, 0.9, it can't be 0.99. Remember, we still have to be increasing it to 0.98. So what does the textbook say? P is 980 divided by 525. I'm pretty sure of that. What do we get? Cos is P is 980, 525. No, man. Opposite? No, it's, yeah, it's adjacent over. Just give me a moment. Let me just get it right here. 5 to 5. Oh, I see the mistake I have here. I'm reading. It's the question. Sorry, guys. It's a mistake I made here. So what it's saying is that yeah, my bad. Sorry about this. Yeah. Okay. So let me get this right here. So it's a quite strange question here. It's not it's not the best one to start with. Okay, so what they say, what is not copied properly here, this is supposed to be volt. So it's not volt amp, and obviously it can't be bigger. So you have power, that, and that. So what they're saying here, this is not an ideal example, but anyway. Yeah. Okay, so what we're looking for is, so they give us, just bear with me, I'm just trying to figure out. It should be before and after. Okay. Just the question is just weird. 0.914. Yeah, just hold on. Please. P is 980. Y I'll take. Oh, okay, cool. I'm following now. Okay. So P is 980, and the saying for this particular thing that there is a both an inductive and a capacitive, load. So to find Q1, it's going to be 960 minus 960 plus 525, right? So reactive load is capacitive load is always positive. So Q1 will be minus 435 watt. So this is actually 435. I see what they're trying to say now. Now what we need to do is actually find this. So this is the first one. So that's what they're actually saying. So tan alpha, which is going to be opposite. So can I get not alpha? Can I get phi now? Thank you. Now I see what they're saying. Because typically they give it a lot different from this. That is why I was like thrown off. Don't forgive me for that. Yeah. So let's get that angle. This angle over here. And it shouldn't be 0. Do we need that angle? I don't even think we need that angle, but that's fine. I'll get it for you. Q is going to be 435 divided by 980. And if you get an angle of 23.95 degrees, and if obviously you want to find the power factor of the first power factor before correction, that's cos phi. So cos of that angle, cos phi 1, and it's 0.914. This is what I'm trying to demonstrate, is that the power factor is 0.914, and we're taking it up to 0.91 to 0.98. Is that clear to everyone? So this is the base case, right? So sorry about that, man. I just fumbled there because I missed that value. So what we're going to do now is improve the 0.918 to the 0.98. So the question is, how much capacitors or capacitance or capacitor value do we actually require? Cool. So going back to this over here, hopefully I can insert a shape which looks a lot better than mine. Right angle triangle. Cool, got one. Where's my rotate? Like that. Okay, I have it here. So what they're saying initially, this was use another color. Maybe this was 435. Yeah, choose a lead. 435, and this is 980. Cool. And what we do now is we are going to improve the power factor. Okay, so I'll use red again. So this angle, so that's another right angle triangle, right? I hope you can see that at least. So Q1 is obviously this whole guy over here. Okay. Oops. Now we want to know what we have to add over here, right? this line over here. Cool. So the first step is we know that the new improved power factor, right, over here. Okay, maybe we should use this black here. This will be alpha 2. So we know now, now we have to find, we know that is 0.98. So we have to say phi 2 will obviously be this, and then you get an angle of 0.98. Okay, so that's 11.478 degrees. So this is 11.478, and this guy was at an angle of 23.98. So guys, can you see what happened here now? So what we're trying to do is now we're going to see how much of this yellow line or the active power we must provide to take this triangle from 23.98 to 11.78. Is that clear? It's quite easy. It's just that it looks a bit, yeah, thanks. I hope you guys get that. Yeah, it's not a real issue. So all we have to basically do is now find, where are we now? We have to find this piece now. So we have to find this new Q. Let me write it over here. So that's Q1. And we have to find Q2 basically over there, which is this triangle of the new thing, and then subtract the 2. So Q2 is quite easy. It's going to be now. And phi 2 is going to be opposite, which is Q2 over P. So P will always stay the same for both. And Q2 will then be P tan phi 2. So that's going to be 780 tan of 11.78. 478, sorry. What is my Q2? Someone tell me. Yeah, it'll be 198.99, right? So there was a negative value. Okay, it's no big deal really. 198.99. Okay, wow. So all we do now, right? And I'm gonna now open up a new triangle. Okay. So all we're doing now is, so Q1 was 435 volt amps, and obviously we found now Q2, which is on top. Okay. Yeah. So let's get the red color here. Okay, cool. So we know that this guy from there to there somewhere is 198.99. Okay, cool. So we need to find the changing Q. So what the changing Q means is how much active power we need to supply now to so I didn't even work with the negative value. So the changing Q is simply the 435 minus the 198.99. Right? You just do that. 435 minus 198.99. You get 236,01 volt amp. So what this is, this over here is basically the changing Q. So we are now, like I said, the yellow line. this here, the capacitors are now producing active power to push this up from here to here. And all you must do now is plug into your formula, and I'll copy the formula for you, and you can actually solve it. So you've got changing Q, and we've got the voltage, and we've got the frequency. So yeah, so the frequency was 60 hertz, voltage is 125. So can you guys quickly solve this for me? Here's the formula. How much capacitance do you require for a single phase? How much capacitance do you need? So the next step is this formula. And give me your C value, please. So it's changing Q, V squared F. Yeah. 40.066 farads or what? Kitongo. Let's have a look. It's supposed to be mu farads, micro farads. Okay, 40.066 mu farads. Remember this, what was in kilo? Yeah. Voltage squared 2 pi f. You guys all do that? And of course, I might ask you what methods you use to provide the active power. I expect you to know that. Or you better know. Just give me a moment. Looking at something here. Okay. Just realize something there. Just looking at my John Bird book, chapter 29. Okay, so our last thing for the day, I'd like you to attempt a problem for me. It's John Bird, page 386, apparently so. Power factor type questions, problem number 7. And they give you a circuit with the impedance, frequency, voltage source, the one current, and then and what they're basically requesting is for you to improve the power factor to 0.966. Yeah, that's why is it? What's sort of C is the oh, so C would be when they say the rating of the capacitor, what they mean is in VAR, and D would be the value of the capacitance, the actual value of the capacitance. So what you first need to do is come up with the current. Once you have the current, obviously, in this case, they give you a voltage at 50 degrees, not at 0. Find the active power, apparent power, and the active power. Obviously, through this, you will get your current will give you a power factor angle, and obviously, your power factor. So, do you want to do this for homework, or we're going to do it now? It was basically done the lecture now. That's all the content for power factor. You guys need to go now. Homework is fine. Okay. Well, guys, without ado, you have a lot of homework for power factor. I'll probably do one to warm up a power factor chapter, a power factor correction sum with you. Then obviously, I think that will be best. And yeah, that's the end. And next week we're going to do resonance, and then I think half the lecture will be resonance, and then we'll start on 3-phase. But 3-phase, obviously, I'll get into, I guess, like an introductory level. And like I said, all these chapters are fairly small. I'll probably start like maybe the first 3 examples or something. So we'll do resonance and 3-phase next week. That is my plan. I can get it right. So I'm typically a slow lecture in terms of breaking content down. But what's important is, once I post the slides, make sure you practice all the problems I recommend. I will post a Word tutorial, a PDF tutorial as well, and I'll post those answers later. So obviously you guys will engage with me. I will see if you guys are responding, and I'll post the solutions once you've obviously attempted at least the problems. Anyway, guys, thank you for attending today. I know it's Wednesday is always a heavy day for you, especially the MBKs. Yeah, make sure you keep practicing. The test, you know, by end of April, you'll essentially be done with electros basically. Anyway, all the best and see you next week.